Times are strange, here I come, but I ain't the same. Mama, I'm coming home. Time's gone by.
Surprise! We're going all the way to section 5.1. Weird, eh? Just seems to make good sense to me. We're going to do 5.1, 5.2, and then we'll return to chapter 1 after that. So we're still going to be talking about limits here, and that's why I thought that I'd do this now. So we're going to be looking at vertical asymptotes, which is something you've talked about before in your mathematics career, and now we're going to talk about it in terms of limits. So what we're going to do is we're going to figure out what's the limit of 1 over x squared as x approaches 0. So in order to do this, let's actually graph 1 over x squared. Okay, we're going to see what that looks like. So let's make a little table. We've got our x and we've got our y, and what our y is 1 over x squared, right? That's how we're going to get our y value by actually plugging it into there. And let's start by putting 1 in there. So if we put 1, we get 1 squared. I guess I can do it here. 1 squared is 1. 1 over 1 is 1. And just to save some time, whether I put plus 1 in there or negative 1, I get the same thing, don't I, since I'm squaring it. So for all our values, why don't we just do that? We'll go plus or minus. Okay, now we want to approach 0. So let's approach 0 by going to 0.5. We're getting closer to 0 from 1. 1 to 0.5. And again, we can do plus or minus. So 0.5 squared that's a quarter basically, and 1 divided by a quarter is 4. Okay, let's go even smaller. Let's go 0.2. And I think I'm going to stop doing the math in my head and I'll just start doing it. I'll do one more. 0.2 squared is 0.04, and 1 divided by 0.04 is 25. Okay, let's go even smaller. Let's go plus or minus 0.1. And if you do that, you're going to get 100. We're getting very, very close to 0 now, aren't we? I've got 0.01 now. And when I put that in there, I get 10,000. And should we do one more? It's a bit ridiculous, but what the heck? 0, 0, 1, and if I do that, I get 1,000,000. So I think it's pretty obvious what's happening here. As we're getting closer and closer and closer to 0, what's happening in these numbers is they're getting bigger and bigger and bigger. So let's just graph this. When the x value is 1, we get a y value, because this is what y is equal to, right? We get a y value of 1. When it's 0.5, we get 4. And when it's 0.2, we get 25. We can't even graph that. But you know what's happening here is it's going higher and higher and higher. It's getting closer and closer and closer to the y-axis, but it's never actually reaching it. Now, what's happening down here? It's not so much of interest to us in this case, because we're trying to find the limit as x approaches 0. But let's just take a look at it. If we put 2 in here, I get 1 over 2 squared, which is 4. I get a quarter. And if I put 3 in there, I get 1 over 3 squared, which is a ninth. And you can see this is getting lower and lower, but it's actually never going to touch the x-axis. So we have a horizontal asymptote there, don't we? Now remember, it was the same thing when we put negative values in. So negative 1, 1 was a point, and negative 0.54, and etc. And so it's just going to look like this. I'll do my best to make it get closer and closer, but never touch. Something like that. Okay? So the question here is, what's the limit as x approaches 0 of this function? Okay, well, we can use our graph here. Let's do it from the left-handed limit first. The limit of 1 over x squared as x approaches 0 from the left. Well, that means we're getting closer and closer and closer to 0 here, right? We want an x value of 0. What's happening is it's getting closer and closer and closer to 0. It's going up and up and up and higher and higher and higher, and we can get, we can make this as big as we want, just get closer and closer and closer to 0. If this isn't big enough for you, if you're not convinced how big I can make it, don't put 0.001 in here, put 0.00000000001. And if you're still not convinced how big the number is, you want even bigger, put even more zeros before the 1. What I'm saying here is basically you can make this number as big as you want. So what's this approaching as we get closer and closer to 0? It's approaching infinity. Now, if we look at this from the right-handed limit, it's a bit redundant because you can see from the graph it does exactly the same thing. As we're approaching an x value of 0 on this graph, this goes higher and higher and higher. How high does it go? As high as we want, all the way up to infinity. hey, left side limit equals right hand limit. That means the limit of 1 over x squared as x approaches 0 is infinity. This is called an infinite limit. So this is when the limit of some function as x approaches a, when that equals infinity, then we have an infinite limit. The way we say this is the limit of f of x as x approaches a is infinity. I think I already said that. Now I've got a bunch of things to write down here, so good luck to you. First one, the values of f of x become larger and larger. We say they increase without bound. Like you can make them as big as you want as x gets closer and closer to a without ever reaching it. Remember, we can't actually go to 0 here, because if you had an x value of 0, you have 1 over 0, which you're not allowed to do. But I can go as close to 0 as I want. Remember, I can go 0.00000, I can put 63,000 zeros before the 1, and this y value is going to be absolutely enormous. And so the values of f of x keep becoming larger and larger as we get closer to a. It does not mean that infinity is a number. Infinity is not a number. So this is a common mistake in calculus. People start dealing with infinity like as a number. They start doing things like 2 times infinity is 2 infinity and stuff. You can't do that. Infinity is not a number. So that's not too confusing, but this is confusing because we've just talked about how this limit equals something, but it does not mean that the limit exists. Even though we're saying the limit of this function right here, even though we're saying the limit is equal to infinity, the limit actually doesn't exist. Now, why doesn't it exist? Because if you remember back to what we had 3 criteria in the last lesson, and the first criteria for a limit to exist is that f of a had to exist. F of a must exist. So in our example here, since our a value is 0, we would need f of a to exist. Sorry, we need f of 0 to exist. Well, when you have an input of 0, an x value of 0, what's the y value? There is none, because x can't be 0. So f of 0 does not exist, which means the limit does not exist. Does not exist. Don't know why I didn't put D and E. Okay, it doesn't exist. So I know it's confusing because we just said that the limit is equal to infinity, but the limit actually doesn't exist. It's more just like a quick way of writing this concept down, but it does kind of confuse the matter because it makes it sound like the limit exists. It doesn't exist. I know I've just said that about 6 times, but I wanted to emphasize that. The line x equals a is called the vertical asymptote, right? You know that already. This line, the line right here, and the equation of this line, this dotted line, is x equals a. Remember, a is 0, so this line x equals 0. This is the vertical asymptote. And the reason it's a vertical asymptote is because the function is getting closer and closer and closer to that line, but it's never actually reaching it. Never going to get there. You can get as close as we want, but never reach it. Okay, now we're going to practically do the same thing. We're going to graph this. We're going to figure out the limit of this function as x approaches 0. And again, the way we're going to do this is we're going to graph this. So let's make our table of values. Now, I don't think we can put plus or minus this time because it's going to make a difference whether we have positive or negative values. So let's use 1. We want to approach 0. So let's go 1, 0.5, 0.1, and 0.01. And then we'll do the same sort of thing with negative values. So we'll go negative 1, negative 0.5, negative 0.1, and negative 0.01. We'll do all those. Okay, so I'm going to put 1 in here. I get 1 plus 5 is 6. 1 to the 4th is 1, so 6 over 1 is 6, and then I have to put a negative on it, so I get negative 6. Now, I don't know, I think maybe I'll just go straight to telling you the answers rather than impressing you with my mathematical ability here. So if I put 0.5 in there, and I do all the math, I'm going to end up with negative 88. Whoa, that's a lot bigger. If I put 0.1 in there, I end up with negative 51,000. You can see we're going up very big, very fast. And then if I put 0.01 in there, I get negative 5, give me a second here, 501 million. Okay, it's a pretty big number. If we go with negative 1, well, we can do this one again. Negative 1 plus 5 is positive 4. Negative 1 to the fourth power is positive 1, so 4 over 1 is 4, and then slap a negative on, you get negative 4. If you put negative 0.5 in there, you get negative 72. If you put negative 0.1, you get negative 49,000. And if you put negative 0.01, you get negative 499 million. 2, 3, 4, 5, 6. Okay, so if we graph this, we have 1, negative 6, we have 0.5, and negative 88. I can't even graph that. So it's getting closer and closer to the y-axis here, and it's coming up. And if we put bigger numbers in here, let's put 5 in here. 5 plus 5 is 10. 5 to the fourth is like 625, so you get negative 10 over 625, which is going to be a very small number. So basically what's going to happen, we're not going to waste time doing this, but it's going to get closer and closer to the x-axis. It's probably much steeper. It probably goes more like this, but I'll just draw it like that. And when I look at the negative values, I have negative 1, negative 4, and then I have negative 0.5, negative 72. It's already way down here. Something like that. Okay, so don't worry about this part of the graph so much. What we're interested in is when we're approaching 0. So as we're approaching 0 from the left-hand side, what's happening to our y values? They're getting small. How small? As small as I want them. If negative 499 million isn't small enough for you, put negative 0.000001 and it'll be even smaller. This is going really, really small. Like how small? Negative infinity. How about as we approach 0 from the right-hand side? Again, those values are getting really, really small. How small? Negative infinity. Hey, left-hand limit equaled right-hand limit, which means the limit itself is equal to negative infinity. So this is the second type of infinite limit. It's when a limit equals negative infinity. Not surprisingly, the way we write that is the limit of some function as x approaches a is equal to negative infinity. So the limit of f of x as x approaches a is negative infinity. That's how you say it. The values of f of x become smaller and smaller, so they decrease without bound. In other words, we can make them as small as we want as x gets closer and closer to a without ever reaching it. And again, does not mean infinity is a number. It does not mean that the limit exists. And again, the line x equals a is the vertical asymptote. So I guess we could draw the vertical asymptote in there again if we want. Obviously, it's right here. Again, this is when x equals a, and a was 0 in this case, right? Right here, 0. So x equals 0, and this is our vertical asymptote again. Okay, so there you go. Okay, now we're going to look at one-sided infinite limits. So on the previous page, this is our regular limits where we're looking at both sides. Left-hand side equals right-hand side. Left-hand side limit equals right-hand side limit. But we also have our one-side limits like we learned last time. So one possibility, because there's 4 possibilities here, one is that the limit of some function as x approaches a from the left-hand side, right? Let's make it a one-sided limit, that it equals infinity. So let's just draw an example of this. So remember, at the point A, we're going to get a vertical asymptote. So let's just draw the vertical asymptote anywhere you want. I don't know. I'm going to put it here at 4. So if this is my A value right here at 4, I'll label it A. Then what would the function look like near the asymptote if we're saying as we approach a from the left, it approaches infinity. Sorry, the function approaches infinity. Well, as we come to the left of this dotted line, it must go up towards infinity like this. The rest of the function, you can do whatever you want. I don't know, I'll curve around a little bit like this. Doesn't matter. This is my f of x. This is the function that has a one-sided limit as it approaches a of going towards infinity. Another possibility is that the limit of the function as x approaches a from the right-hand side equals infinity. So again, just draw your vertical asymptote anywhere you want. It doesn't matter. You can put it at the same spot. You can put it somewhere else. I'll put it slightly different this time. I'll put it at 2. It makes no difference. And what I'm saying this time for the function, again, this is a. That's where my asymptote is. What I'm saying this time is I approach a from the right-hand side the function's going to approach infinity. So in other words, it's going to go up towards infinity on this side this time. Rest of the function, it doesn't matter. I'll just do this time. Okay, that's fine. Okay, let's do the third possibility, which is the limit of f of x as x approaches a from the left-hand side equals, what's going to be different this time? It's not going to be infinity, it's going to be negative infinity. So pick a spot for your vertical asymptote. I'll pick here. I don't know, pick wherever you want. This is my a. As I'm approaching it from the left-hand side, so over here, it's going to go not up to infinity, but down to negative infinity. So it goes down to negative infinity like this. And maybe it just goes like that. Doesn't matter. The rest of the graph really doesn't matter, right? The part that matters is close to the asymptote. And of course, the final one, hopefully you can figure it out for yourself, would be the limit of f of x as x approaches what? X approaches a from the right-hand side, again equals negative infinity. So let's draw our asymptote. I'll draw it here. So this is my a. That's what the asymptote is. I'm approaching it from the right-hand side, and it's going down towards infinity, so it should be going something like that, down towards infinity. Rest of it doesn't matter. I'll do it like this. Okay, those are your 4 possibilities for one-sided infinite limits. In all 4 cases, the line x equal a is the vertical asymptote, just like we've drawn it there. That's your vertical asymptote. Okay, now we're going to find some one-sided limits, and then we're going to find a regular limit that's not one-sided. And what we're going to use to find this is something that I call fuzzy math. Right? It's not exact math, it's approximate math or fuzzy math. Okay, you're not going to get exact values for this when you're doing this. It's a bit strange when you first do this because we're so used in math to always having exact numbers that we're dealing with. So here's the way we're going to do this. We're looking at this first one here. It says find the limit of 2x over x minus 3 as x approaches 3 from the, I can't even read that, that's a plus there, from the right hand side. Okay, so that means just a tiny bit bigger than 3, right? That's like 3.00000, as many zeros as you want, 1. Tiny bit bigger than 3. So on the top, if you multiply 2 times a number just a tiny bit bigger than 3, you're going to get 6 point something. I don't know, 6 point, and I'll put a line to show there's something else there. Over, but it's basically 6. It's so close to 6 that, you know what, when we do the fuzzy math, let's just call it 6, just to make it a little less fuzzy. On the top, you can just call it 6. 2 times 3 is 6. On the bottom, you can't do that, because if you use the actual number 3, you're going to get 3 minus 3 is 0, and you can't put 0 on the bottom, because 6 divided by 0 you're not allowed to do. So here's where we use our fuzzy math. We have a number that's a tiny bit bigger than 3, right? 3.00001. Then I'm going to subtract 3. What am I left with? I'm left with 0.00001 or whatever. Basically what I'm left with is a very, that's V for very small number. Is it a very small positive or a very small negative number? It's a very small positive number, right? I'll go through that one more time if you didn't understand. If I take a number just a tiny bit bigger than 3 and subtract 3, I'm left with a very tiny number, and it's positive. So now what I have to do is I have to divide 6 by a very small number. So what happens when I divide 6 by 2? I get 3. What's 6 by 1? 6. What's 6 by 0.5? 12. See what's happening? It's going up and up and up. What happens when I divide 6 by 0.1? It's 60. What happens when I divide 6 by a very small number? I get a very big positive number. I'm going to start using the number sign to make things faster. Okay, how big can we get this number? As big as we want. In other words, we're going to end up with the limit of 2x over x minus 3 as x approaches 3 from the right hand side. Which value, or what should I write down here for my my answer here? My answer is I can get it as big as I want. I can make it positive infinity. Let's do another one. It's going to be quite similar. So we're going to do the limit of the same thing, 2x over x minus 3, as x approaches 3 from the left-hand side. So on the top, you can get really close to 3. In fact, you can just put 3 in there. We're going to get 2 times 3 is 6. On the bottom, you can't put 3 in there because 3 minus 3 is 0. So you got to think about this. It's a little bit to the left of 3, a little bit smaller than 3. So we're talking 2.9999999, and we're subtracting 3. Where are you going to end up if you subtract 2.99999 something minus 3? You're going to end up a tiny bit below 0. You're going to end up with a very small number. What kind of number? Negative number this time. Okay, if we divide 6 by a very small negative number, what kind of answer do you get? Well, 6 divided by negative 1 is negative 6. 6 divided by negative 0.5 is negative 12. 6 divided by negative 1 is negative 60. It's just like what was happening over here, except all the answers are negative. So we're going to get a very big, they're getting bigger and bigger, negative number this time. How big can we make it? As big as you want. Well, actually, it's this big negative, which means it's a very small number. So what you end up with is that the limit of 2x over x minus 3 as x approaches 3 from the left is equal to negative infinity this time. So, by the way, what would you say about, I hadn't written this down, but what's the answer to the limit of 2x over x minus 3 as x approaches 3? We have the left-hand limit, we have the right-hand limit. What's this equal? D and E, because they're not equal to each other. If you were to just sketch this super quick, like I really don't know what it actually looks like, but if I was to go to 3, 1, 2, 3, because that's my A value, and if I put an asymptote right there, right, that's the asymptote, what would it look like? Well, from the left-hand side, which was this one, it went towards negative infinity, so it went like this, and I don't know what happens to the rest of it. I don't really care right now. And from the right-hand side, which was here, it went up towards infinity, like this. Okay, another one where we're going to use fuzzy math. So this time it asked for the limit of this huge function as x approaches 5. Well, we can't do that in one go. We're going to have to actually look at the one-sided limits. So we're going to have to look at the limit as x approaches 5 from the left-hand side of this big function. And we're going to have to do the same thing for the right-hand limit. So let's do that now. If I put 5 in here, I can keep my 4 minus 3 is fine. Okay, I can't put 5 here because you would have 5 minus 5 is 0, and 0 squared is still 0. So we've got to use our fuzzy math. We have a little bit smaller than 5, right? Left-hand side of 5 is a little bit smaller, like 4.999, and I'm subtracting 5. A little smaller than 5, subtract 5, I'm left with a tiny negative. So I'm going to put small, or very small, but I'll just put small negative, but I'm squaring that. So then what I'm going to end up with is 4 minus 3 over. Now, when you square a small number, like 0.5, what happens when you square 0.5? You get 0.25, which is even smaller. If you square 0.1, you get 0.01, which is even smaller. So if you square a small number, you get an even smaller number. Okay, so I'm still going to have a small number. Now, is it going to be a small negative or a small positive? Well, you're going negative times negative, right? You're squaring a negative, so it's going to become a small positive. All right, nice. So still we have 4 minus, now 3 divided by a small number. Remember, this is really small. It's like 0.0001. So what happens when you go 3 minus an extremely small number? You're going to get used to this happening. It happens all the time. Dividing by a really small number gives you an enormously large number. How big? As big as you want. So you end up with 4 minus a large, like very large, positive. Okay, now you've got 4 and you're taking away a large positive. Remember, this is a really large positive. We're talking bigger than billions, trillions, quadrillions, whatever those big numbers are called. So where you're going to end up if you go 4 minus an extremely large positive, like as big as you want that positive to be, you're going to end up down at negative infinity. So our answer for the left-handed limit is negative infinity. Then what we'd have to do is we'd have to do the right-hand limit. The limit of x as x approaches 5 from the right-hand side of this same function, 4 minus 3 over x minus 5 squared. Now I'm hoping you see that it's going to end up being exactly the same thing. Why? Because if I did the fuzzy math here, I'd have 4 minus 3 a tiny bit bigger than 5. A tiny bit bigger than 5 minus 5 equals a tiny number. What kind? Tiny positive or negative? Positive. And then we're going to square that. Well, here we have a small negative squared, and here we have a tiny, I should have put small again, sorry, small positive squared. That gives you the same thing because you're squaring. You end up doing exactly the same thing as you go through here. From this stage on, it's exactly the same. So again, you're going to end up with a negative infinity. So you have your left-hand limit equals negative infinity. You have your right-hand limit equals negative infinity. What's that mean for the limit overall? It equals negative infinity. Because these two equal each other, we can say that the limit is negative infinity. Remember, this does not mean that the limit exists. It just shows that it does not exist, actually, but there's a special way it doesn't exist. The special way it doesn't exist is that it approaches negative infinity in this case. Okay, last one is we're going to find the vertical asymptotes of this function, and then we're going to sketch the graph near the asymptotes. Okay, to find vertical asymptotes, you did this in grade 11 and 12. You take a look at the denominator and you ask yourself, what would make the denominator equal 0? And the easiest way to do this is to actually factor. So we're going to keep our x on top, but on the bottom we can factor this. Simple trinomial. You end up with x and x. Two numbers that multiply to 15 and subtract to 2 are 5 and 3, so we get plus 5 and minus 3. And now, if we were to start sketching this, for example, we would have two asymptotes. One would be at positive 3, and the other one would be at negative 5. So I'm going to draw those in right now. And what we want to know is, what does the graph do near these asymptotes? Now, we know it's either going to go to infinity or negative infinity, but we're going to have to look at 4 different one-sided limits. We're going to have to look at the left-hand side of this asymptote, the right-hand side of this asymptote, the left-hand side of this asymptote, the right-hand side of this asymptote. I'm sorry, everyone. I know it's a lot of work, but that's what we're supposed to do. So let's do it. Let's start by looking at the limit of the function g of x, because that's what it's called, right, as x approaches negative 5 from the left. And if you do that, what you're going to get is, well, we can just plug negative 5 in here. That's fine. Okay, we can even, so I'm going to put a bracket there. We can even plug negative 5 in here. Negative 5 minus 3 is negative 8. That's fine. But here we can't plug negative 5 in, so we're going to have to use some fuzzy math. So we have a little bit to the left of negative 5, a little bit smaller than negative 5, and then we're adding 5. What are you going to end up when you do that? You're going to end up with a small negative. Okay, so let's keep the negative 5 here. And then we have a very small number times negative 8. Small negative times negative 8. Well, it's going to be positive, right? Because negative times negative is positive. And this is extremely small, remember. 0.00000, like 63 zeros before the 1. If you multiply it by negative 8, what kind of number are you going to get? It's going to be small. So you end up with negative 5 divided by a small positive. Negative divided by positive is negative, and 5 divided by an extremely small number is very big. How big? Well, you could make it infinity. So negative infinity is going to be your answer here. So as we approach negative 5 from the left-hand side, the graph is going to go towards negative infinity, something like this. Okay, now let's find the limit of this function as x approaches negative 5 from the right-hand side. Well, again, we can put negative 5 in the numerator right here. That's fine. Again, for the second bracket, we can do negative 5 minus 3, which is negative 8. But for this bracket, what do? We have to use fuzzy math. So a little bit bigger than negative 5, so it's like negative 4.9999, and we add 5. Where do you end up with there? We end up with a small, very small, positive this time. Okay, let's see if we can skip a step here. We have negative, positive, and negative, so we're going to end up with a positive. And this tiny, tiny number times negative 8 is still going to be very, very, very small. And negative 5 divided by this very, very small number is going to become very, very big. We're going to end up with positive infinity. So this time, as we approach -5 from the right-hand side, our graph is going to approach positive infinity like this. All right, let's now do the limit of g of x as x approaches 3 from the left-hand side. So again, we can just plug in here 3 on the top, and we can just plug 3 in here. 3 plus 5 is 8, but now we got to use fuzzy math. We're approaching from the left, a little bit smaller than 3, and then take away 3. So it's 2.9999, take away 3, what do you get? You get a very small negative. Okay, we got positive, positive, and negative, so it's going to be negative. And 8 times a very, very small number is still a very small number. 3 take away a very, very, very small number is going to be a very, very big number. How big? As big as you want. It could be negative infinity here. So from the left-hand side of this, it's going to approach negative infinity like this. And finally, the limit of g of x as x approaches 3 from the right-hand side. So we can plug 3 into the top. We can plug 3 in here, and we get 8. Got to use some fuzzy math. Tiny bit bigger than 3, 3.0001. And we subtract 3. What kind of number you get? You get a very small positive. All positive, so our answer is going to be positive. 8 times a very small number is still a small number. 3 divided by a small number is a very big number, as big as you want. So it's going to be positive infinity. So on this side, it's going to go towards positive infinity. Another really easy point to get, just to finish this graph off, is to get the y-intercept. So if we get a y-intercept, you put 0 into the x. 0 here, divided by 0 plus 0 minus 15. 0 over negative 15 is 0. So we know the graph goes through here. So it turns out it's going to look something like this. There's probably a little more here we'd have to deal with. Might come down like that, up like that, but we won't worry about that. There you go. There's our graph. Specifically near the asymptotes. That's what we wanted to know. This is a very important concept. We'll be doing lots more of this near the asymptote sketching later on in chapter 5, I believe. Okay, thanks very much, everyone. Bye-bye.
Selfish love, yeah, we're